we are going to switch over to Pontus Brandt, who's going to talk about science operations, trades, conclusions. Pontus, the floor is yours.
Thank you very much. Let me share my screen. There we go. And yes, so I only have 3 or 4 slides. I want to make this relatively short to leave room for questions. But I just noticed that we have currently 492 members on the website. Thank you for signing up. This is really, really close to 500. Wouldn't it be nice to have 500 by the end of this workshop? I'm just saying. So go to interstellarprobe.jhuapl.edu and please sign up. Oh my goodness, this sounds like a commercial. All right, let's go on. All right, let me get rid of some windows here so I see what I'm my own slides. So first I'm going to take you through the sort of high level thinking on the operations here, and then have some concluding thoughts on the trades that we've sort of gone through the past 2.5 days now. So what you see here is our foldout on the mission science investigations at large, and I think the main message here is that operations start already after instrument commissioning, shortly after launch, right? And as you already saw, I mean, this starts with, well, as I like to say usually, is that the heliospheric boundary and the heliospheric dynamics and the formation of the boundary already starts deep inside the heliosphere. And that is because we have this penetration of interstellar neutrals and the subsequent formation of the pickup ions that then mediate the solar wind and heats also the solar wind via wave particle interactions, and then gets back out to the boundary where it turns out it's the dominating energy density that upholds the entire heliosphere. So up here you see basically all the objectives and investigations that we have in the science traceability matrix, and this is still a preliminary foldout that we have, but this is where we graphically point out where we're going to do this investigation. So it's a pickup by ion evolution, as I said, coupled also with the solar wind transport and acceleration, of course, going out and also looking at the interstellar neutrals with Lyman alpha and in situ, and look into not only remotely what the interstellar neutrals are doing at the boundary, but also the filtration of neutrals as we go out. With the current sort of trajectories that we have, the termination shock will be reached in about 12 to 14 years, depending exactly what direction, and of course, where the termination shock is, because that heavily depends on the direction. We only know where the termination shock was for the Voyager crossings, of course. Out there in the heliosheath, of course, force balance, and ENA imaging and also Lyman alpha imaging, going out, doing this from a changing vantage point is extremely important, and also starts very deep inside the heliosphere. And already after 1 year or so, to give you perspective, we should be able to start seeing a changing sort of view angle of the ribbon, for example. So that's relatively quickly. Heliopause will then be reached in about 17 to 29 years, depending on the heliopause estimates and where it really is. Heliospheric dynamics, of course, is an investigation that goes throughout of it. And then the extent of the solar disturbances, of course, is way beyond the heliopause. Then after about 20 to 43 years, that's probably when one would expect to reach and figure out if there is some kind of bow wave in front of the heliosphere, and coupled with that is, of course, the hydrogen wall. And already starting at the heliopause, that's where we get into this the unknown sea, or the mare incognitum exploration of this completely new properties of the interstellar medium that we haven't seen before. There's been a lot of talk about the unperturbed interstellar medium. The Voyagers, they are of course in the perturbed interstellar medium because they already they still see shock propagation out there. They see changing anisotropies and galactic cosmic rays, of course. Estimates out there put the unperturbed very local interstellar medium somewhere, I'd say around maybe 600 AU or so. And of course, as we stated, the mission design relies on a 50-year design lifetime. But given that Voyager has already outlived its lifetime, but by about an order of magnitude, it is very likely that we will also survive, even perhaps out to 1,000 AU. Who knows? Also here, so that was the baseline heliophysics science as we're thinking about it, and we're dividing that into three very big phases. It's of course the inner heliospheric phase, the heliosheath phase, and then the interstellar phase. The cross-divisional augmentation is fairly simple in a way. Astrophysics, those have been sort of the ride-along group all along. They'll pick up the measurements of in the infrared spectrum of the circumsolar dust disk and the extragalactic background light. Already with extragalactic background light starting already at 10 AU, or perhaps even at 5 AU. Planetary science, the KBO flybys goes without saying, but of course. I do have a sneaky suspicion that the Kuiper belt is expanding the more and more we look at it. Here we've drawn it out to the termination shock, and who knows, there might be objects perhaps even beyond that. We don't know. All right, so let me go into sort of the more detailed mission operations part of this slide. So as I said, after launch, we do checkout, we do boom deployment, and I think also Jim will of course talk about this, I think tomorrow. And then if we have a passive Jupiter gravity assist, we can do the 50-meter plasma wave wire antenna deployment, because as you know, I mean a passive Jupiter gravity assist is more or less just a free fall. The only other thing there is just tidal forces that would act on it, but those would be negligible. However, if it's a power gravity assist, gotta wait with the wire antenna deployment until the Jupiter gravity assist, and that's why we would also have the 2.5 meter root stasers for the augmented mission. Okay, and then we commence sort of the more bulk or prime mission operations, if you will. I have it outlined here in the upper right, just so you can see it more clearly. I wouldn't say simple, but we're requiring continuous operations. As I said, the science investigation starts already just shortly after launch. There is, for the heliophysics baseline, of course, there's no specific pointing requirements. We're not really relying on any specific mechanisms. It's worth a note that the stepping motor on LSCP on Voyager still works. However, we're trying to, in this study, to sort of veer away from mechanisms. The operations, the instrument operations as we see them, they should be, I think it's smart to have them self-contained, such that we don't really have coupled instrument operations, but stick to a more simple operations scenario rather than a very complex one. This is not an MMS mission at Earth trying to look at the reconnection scales, of course, but this is more of an exploration mission, and coupled with reliability, we got to keep it simple. Parameter uploads for instruments, do think those are infrequent, and perhaps when we cross over to other boundaries, they become more frequent. But the important thing here is we do expect to have a rather large mass memory on board, such that instruments they can produce both low resolution data and very high resolution data, and they put that down on the recorder. And then what you do is you look at the low resolution data stream on ground, and that's a low resolution good enough for writing scientific papers on. But if you see any events that you want to have high resolution data on, you go back and you ask the spacecraft to send back this chunk of high resolution data. So in that sort of sense, you maximize the science output by utilizing what we call selective data downlink. Okay, and at the very bottom here, I'm going to skip the data rates here because I think also Dave Copeland will talk some about this tomorrow. At the very bottom is the generational succession plan. I mean, a lot of this is serious. A lot of folks sort of dance around it in a sense, but the further we explore out there, the more and more serious that becomes. It needs to be a core part of the planning. It needs to be a core part of the budget, because that's not cheap to have people overlapping and having a succession plan in place, and also to implement and then carry out. Okay, let me go to my very last slide, and that's the science trade conclusions, trying to wrap our arms around this. We talked about, of course, three big things here. We talked about the baseline and the augmentation. We talked about the trajectory trades, and we talked about the instrument trades. So in terms of the baseline versus the augmentation, and again, that is of course not our decision to make. That will be NASA's decision, and it will be foremost also the community's decision. So for that high-level trade, it's of course an impact. It's a moderate impact to heliophysics, but that again, that's up to the heliophysics community. There is big cross-divisional value, mind you. Of course, Kirby and also Mike Zemkov will talk about this later today, 11:20. So this is, as I said before, it's a mission level science value with a very moderate contribution in terms of instrumentation. There is also, of course, an impact to the mission architecture. Jim will talk about that tomorrow. It is somewhat to my surprise, it wasn't a big impact as I thought it would be. And also lastly under here is of course the impact to the cost of the NASA divisions, and Kathy will touch on that on Friday. In terms of trajectory trades, it's the launch year foremost, and as I said also, and Aleida presented very well, is when we go to the Solar and Space Physics Decadal Survey, we have a good case that the launch opportunity opens in 2036, and not very much later. So that in a sense makes this very timely for this upcoming Solar and Space Physics Decadal Survey. Distance, obviously, as I already said, speed is another one, because that also dictates the flight time to different targets. And also, as alluded to, accommodation. Depending on where you go, you gotta angle your instrument slightly differently. But that's a very sort of benign trade or impact in my mind. The last one here is the ground station visibility that was also brought up yesterday. You can't really expect to go much lower than your -20 degree south or so because of ground station visibility. You have to keep that in mind. On the instrument trade side, obviously accommodation, somewhat also reliability. The further you make instruments complicated, you also have to keep in mind your reliability program here, and making sure that you can do your accelerated lifetime testing for a 50-year mission. I mean, how do we do with that? We got to keep that in mind when we build our instruments. And I think most importantly, so for reliability, Clay will touch some of that on Friday. Last one here, instrument development. So in the mission concept report, we have asked everybody to summarize the sort of desired optimizations and enhancement that you can do to instruments, such that when NASA reads our mission concept report, they can pick this up and perhaps and hopefully announce an instrument development or optimization program for instrumenters and experimentalists out there. So that sort of summarized at least my thinking on the trade space coming from a science perspective. And I think I will conclude there and leave then 5 minutes for discussion. Thank you.
All right, thank you, Pontus. Any questions for Pontus here? There's a question that's come into the chat. Niben from the previous discussion actually provided the links to the findings that he mentioned. Thank you very much for that, Niben. And I've captured those web pages, Elena, and I'll make sure we got them, okay? We have a quieter audience today. Pontus,
Oh,
actually,
go ahead.
I was going to say, well, thank you for making a point to invite people to the website, to the mailing list again. Andrea informs us, so we're up to 499. Actually, Pontus, could you put your slide back up that showed the timeline of the mission?
Oh yes, I will. Not this one. All right. I'm sort of refreshing that all along.
It's all right.
All right, here we go. Let's put these back up. All right.
Thanks. This is actually, is this taken directly out of the current draft of the report, or is this a modified version of that?
This is the current draft. Yeah, this is the intermediate draft, version 2.
Thank you. I love this view because it shows the different threads of science and where they occur across the whole timeline of the mission. I thought that for folks online, it might be good to ask questions as we solicit for questions on this topic, to be able to see this area here. And one of the things that really kind of evolved over the course of the study was that the first 10 to 12 years of the mission would be sort of inside of the heliosphere, and the next chunk of time, somewhere on the order of 10 years or so, would be in the heliosheath, in that transition region between the inner solar system and the outer, between being inside of the solar system, so to speak, and outside in the interstellar medium. And then beyond that, first 20 to 25 years of flight would be outside in the interstellar medium itself. So Marshall asks if Pontus can post his slides. Yes, Marshall, all the slides will be up on the website itself as we go through this. We talked about this a little bit earlier. When you go to the website, each of the talks has a little plus sign. Not yeah, I know that they're not there now, Marshall. They're going up as we finish them off and post them, probably within a day of the talk itself. Thanks.
Yeah, Andrea says they're already available. Maybe this is the same problem I had. It's just
I'm double checking now.
Okay, thank you.
Thanks. I know that it's automated, Andrea. Once they go up, it takes a little while for it to refresh. So Pontus, Niben has asked, is there any reason why solar wind gets slowed down and cooled near the heliopause?
Absolutely. Yes, absolutely. I'm glad you asked. This is very intriguing, actually. So it has to do with the penetration of the interstellar neutral material into the heliosphere. And once they get closer to the sun, they photoionize. Of course, there's also electron impact ionization and charge exchange involved, but more or less photoionization. So think about then the expanding solar wind are picking up these newly ionized atoms. And it could be anything from hydrogen up to heavier atoms. And once it does that, it mass loads the solar wind. And basically the solar wind energy is put into the pickup ions such that the solar wind is actually slowing down as well. And sure, so if you only have a naked solar wind and expands out adiabatically, it would cool down in a sense. But what also happens here is that once these pickup ions, and now we get into plasma physics, once these pickup ions get picked up, they have a very perpendicular pitch angle distribution around the magnetic field lines. And what happens is you get wave particle interactions that seem to isotropize these pickup ion distributions. And what happens in that process is that the energy from those pickup ions also affect the temperature of the solar wind itself. So you have this very tightly coupled mediation of interstellar matter, not only in form of pickup ions, but it also couples back to the original solar wind as well. So sorry, maybe a long-winded answer, but it's a very intriguing physics.
And measuring it in situ will be the key. Yes?
Yes.
Yes. So, all righty, very good. We are now at 11:10, 11:11 actually. Thank you all for your questions. Niven compliments your answer here, Pontus, saying it was a crystal clear explanation. Thank you. Plasma physics and thermodynamics. You're taking us all to school, Pontus. And right now we're going to take everybody to a break. We'll be back at 11:20 when Kirby Runyon is going to come back and talk about interstellar probe and flybys in the outer solar system. Thanks, everybody. We'll see you at 11:20.